So hello everyone, let's continue our analysis of basic AC circuits, and here also I have a couple of interesting problems for us to see. So this is a basic thing, three elements R, L and C are given. Firstly they are connected in series and later they are connected in parallel. So for each of this case, the voltage is 100 volts 50 hertz AC supply, and find the total impedance, current and complex power in each case. So let's get started with that. So first, consider the series case. So, case where series connection. So, I draw the circuit. So, it is something like this. This is a capacitance, and then this is uh, the supply voltage. So, this is 100 volts, 50 hertz AC supply, and the resistance is 12 ohms. And here, the inductance is 0.15 henries and 100 microfarads. So first we begin by calculating XL. So that will be nothing but j omega L. That is nothing but j into 2 into pi into 50 frequency given in the question into 0.15. So this is the one value. Then XC is nothing but 1 by j omega C. So that is 1 divided by j into 2 pi into 50 into 100 microfarads. So I'll put 10 to the power of 6 in the numerator. So let's do quickly these two calculations and come back. So I'll use my calculator. So first is XL. So I'll write XL equal to 2 into pi into 50 into L. So the L is 0.15 henries. So I'm getting 47.12, and also note I should put I here. So I into this. So I get J 47.12. So, J 47.12. What about XC? So XC is 1 by j omega C. So let's calculate that. So XC equal to 1 divided by I into 2 into pi into 50 into C. So that is 100 E minus 6, 100 microfarads. So I get minus 31.83 J. So let me go back this, minus J 31.83 ohms. Now if you look at the series connection, we have to add them. So the reactance is, magnitude wise reactance is more than the inductive reactance is more than the capacitive reactance. So therefore, overall this will become an inductive circuit. So let's do that. So what is my overall impedance? So impedance is 12 plus, so basically impedance is R plus XL plus XC. So that is nothing but 12 plus J 47.12 minus J 31.83. So let's do that. So R is equal to 12 and my Z is nothing but R plus XL plus XC. So I'm just adding all of them. So I get 12 plus J 15.29. So that's what I'll write it here. 12 plus J 15.29 ohms. So this is my total impedance. Now I might express this in the form of polar coordinates. So that is 12 plus J 15.29. Let's say ABS of Z, comma. So I just display both as a matrix, angle of Z. So this I'll multiply by 180 and divide by pi. I do this because I want to get it as a uh, angle in radians. So I'm getting like this, 19.44 I'll take it, and then 51.88. So this is the impedance, 19.44, and the impedance is, sorry, 51.88. So notice the angle is positive. So why angle is positive? Because here it is inductive reactance. So this is positive. So now it is straightforward to find the current. The current is nothing but V by Z. So that's nothing but 100 angle 0 degrees divided by 19.44 angle 51.88 degrees. And that will give me the current. So let's do that. So 100 divided by 19.44. That is 5.144. This is the magnitude of the current and the angle of current is minus 51.88 degrees. So this is in amperes. So this is about the series connection. What else do we need to find out? Find the total impedance, current and complex power for each case. Okay, so now I have the current. So complex power is nothing but V into I conjugate. So this is the formula for complex power. So V is 100 angle 0 degrees multiplied by 5.144 angle minus 51.88 whole conjugate. So the conjugate symbol nothing but you change the sign of the angle. If the angle is negative, make it positive. If the angle is positive, make it negative. So I get 100 angle 0 degrees into 5.144 angle plus 51.88 degrees. So this total will be 514.4 at an angle of 51.88 degrees. Now this one, this is volt amperes. So typically the complex power is again a complex number. It's typically represented in the rectangular form. So rectangular form I'll have watts and wars. So how many watts and how many wars? So let's calculate that. So 5, we can actually multiply V and I. So here, if you recall, I have my Z as a variable. So simply I define I. So capital I is nothing but V divided by Z. So whereas V is, so let me define V. V is 100. So capital I equal to V divided by Z. So I am getting the current. So this is the polar rectangular form of current, 3.17 minus J 4.04. So I might even write it here. So 3.17 minus J 4.04 amperes. This is the rectangular form of current which is same as 5.144 angle minus 51.8. Okay, let's calculate now power. So S is nothing but V into CONJ, conjugate of I. So this is the formula. So then I get 317.57 and 404.71. So I'll write it here. 317 and then plus 405. So I'm just rounding off to the nearest term. So 317 watts of active power is consumed and 405 watts of reactive power is consumed by the entire circuit of RLC connected in series. Now let's do the same problem now considering a parallel connection. Okay, so let's come back here. Case B, that is parallel connection. So I have the same elements, resistance, inductance and reactance, capacitance I mean to say, and the voltage is same, so that is 100 angle 0 degrees. Now to find the total current, so this is 12 ohms, this is because the frequency of the supply is same, the values will be same, 47.12 and 31.83. So this will be J 47.12 ohms and then J minus 37 point, what was that? 83, 31.83. Only thing is now they are connected in parallel. So I can individually find the currents here. So for example, I can find current I1, I can find current I2 and I can find current I3. And then I can add all the currents to find the total current I. And from that I can find the total impedance just by dividing that. That is one way. Other way is you just, as you know, the impedance of parallel circuit is 1 by Z1 plus 1 by Z2 and 1 by Z3. So you can do both ways. So yes, maybe I'll do that. So for a parallel impedance network, so you know that the total impedance, the reciprocal of total impedance is nothing but the reciprocal of 1 by R plus 1 by XL plus 1 by XC. So from this, if I just invert all this, I can find the ZT. So from this implies that Z total is nothing but 1 by R plus 1 by XL plus 1 by XC whole to the power of minus 1. So I think we'll do this first. So I'm just clearing the screen. Just let me check the values. XL value is available, XC is available, and R is also available. So ZP. I'm using the notation ZP because parallel impedance. So that is 1 by R plus 1 by XL plus 1 by XC. So and then overall I have to divide by 1. So I just give 1 by. I can also give to the power of minus 1, but it's both same. So I'm getting the total impedance. Now you notice something interesting. The impedance is negative. The reactive component or the imaginary component of the impedance is negative. That means it is capacitance. It will acting like a capacitance now. So let's see. 11.8 and 1.446. So ZT is 11.8 2 minus J 1.446. So I have the total impedance now. Now it's straightforward. Now I can find the current. It's nothing but V by Z. So same Ohm's law will apply. So V is also defined. So simply V divided by ZP will be my IP, the total current in the circuit. That is 8.333. So this I am getting in the form of reactive current. That is a rectangular representation. 8.33 plus J 1.02. I'll just round it off to this. This is in amperes. Now this one I can also show it in polar form. So how do you get it in polar form? Simply I just make a small two element matrix. First element is absolute value of IP and the second element is angle of IP. This which I convert into degrees. So 8.395 is the amperes. This is magnitude of current, and 6.97 degrees is the angle of the current. So the angle of the current is positive, which means the circuit is capacitive. Now, what else is required? Complex power. So how to get the complex power? So complex power, again it is same, V into I conjugate. So let me do that right away here. SP. So complex power in the parallel circuit is V into CONJ, conjugate of IP. So I'm getting 833 watts minus J 102 watts. So you notice this is the power consumed by the circuit. So if the power consumed by circuit is active power, 833 watts is being consumed already here. Whereas total watts actually supplied by the circuit. So this minus indicates that total watts going from the load side to the supply side. That's why the sign is negative. 102 watts is being supplied by the load to the source. Now, to get this understanding a little bit further, let me draw the same circuit in a slightly bigger notation. So this is the resistance, and this is the reactance, and this is the capacitance. Now, for all the three branches, they are all parallel. The voltage applied is same, 100 volts at an angle of 0 degrees, and this is 12 ohms, and this is J, how much was that? We basically completed the problem, but then I'm just explaining further to make some new point. And this is minus J 31.83. So the impedances are given. Now, if I want to know what is the current here, so just simply this is a parallel branch, nothing to do with other branches, 100 by 12. So if I just divide 100 by 12, I get 8.33. So here 8.33 amperes of current is flowing, and the angle will be 0 degrees. This is I1. What about I2? So because J is there and J will divide by 100, so if I want to find I2, V by XL, that is 100 angle 0 degrees divided by 47.12 angle minus 90 degrees. Why minus 90 degrees? Because, sorry, this is plus 90 degrees, but then it will go into numerator and becomes minus because division of this. So in fact I can do it right away. So V divided by XL. So this is 2.122 purely reactive current, 2.122 amperes. So minus, so let me write it, 2.122 angle of minus 90 degrees. So whereas this current, how much is this current? So I3 is in amperes. So whereas I3 is V by XC, that is 100 0 degrees divided by minus J 31.83. So let's do that. V divided by XC. So I'm getting 3.14159. So that's the current. 3.14 amperes of current, and this one the angle will be plus 90 degrees because here it is minus in the denominator, so it goes to the numerator, it becomes plus 90 degrees. So this is my I3, that is 3.14, angle is plus 90 degrees. So as a result, these two vectors are pointing opposite each other. So this is pointing downwards, this is pointing upwards. So let me draw the vector diagram for this. So by the way, I1 is nothing but V by R, that is nothing but 100 angle 0 degrees divided by 12 angle 0 degrees, basically resistance. So 8.33 angle 0 degrees amperes. So if I draw them as vectors, so this is my first vector, that is 8.33. This is I1, angle is 0 degrees. The second vector pointing upwards. Sorry, I2 is pointing downwards. 2.122, angle is minus 90 degrees. This is I2. Now I3 is pointing upwards. This is slightly taller in length. So this is I3, 3.14, angle is plus 90 degrees. So what is the resultant current? So it is nothing but I1 plus I2 plus I3. So the resultant current will be something like this. So this is I1. Now what is the net value of this? So if I calculate this, this is going up, and then if I come down, so I just come down, this is 2.12. So this one will be the resultant, and that resultant will be something like 3.14 minus 2.12. So I get like this 1.02. So that 1.02 I'll just add it here. So this will be 1.02, and finally I'll get this current as the IT. So which we already calculated above. So you see here in the previous in the parallel connection itself, you see the current that we got here 8.33 and 1.02. So these two numbers we are confirming once again. What is the values? Now, what is the direction of active power? So active power P is going like this. starting from the source and then consuming like this. How much of reactive power is this one consuming? So you see I square into x. So 2.12 square into this one for 47.12. So if I multiply this, then I'll get the active power consumed by the inductor. So let me do that. So that is 47.12 into 2.122 square. So 212 watts. So the active power consumed by this. So active power is typically represented by arrow like this. So with a line, 212 watts are consumed. But this is the source of active power. So capacitor gives watts. So how much capacitor is giving the watts? So you see 3.14 I square x here I have to do. So 3.14 is the current to the power of 2 multiplied by the impedance of that. So the impedance is 31.83. So 31.83. 313 watts. So 313.8. So or 314 watts. So the total watts supplied by this is 314 watts. So out of the 314 watts, 212 watts are being consumed here. So the remaining watts going back to the supply. So you notice 314 watts are coming out of capacitor, 212 watts are going into the inductor. The remaining watts, volt ampere reactive, is 314 minus 212, so 102 watts. So this net power it was as we calculated 833. So therefore from here the complex power is 833 minus J102. So why this minus sign is coming here? Because the net circuit is capacitive, so it is coming like this. Okay, so I hope you understood this. We have taken two cases, that is series case and a parallel case, and then we try to understand this. So also a short vector diagram also I have drawn. Let's continue very quickly. We'll see one more question. So the question is like this: two circuits with impedances Z1 and Z2 are connected in parallel. If the supply current is 20 amperes, what is the complex power consumed by each branch? So let's see how to solve this. It helps if you draw the circuit diagram. So the circuit diagram is like this. This one is an impedance 10 plus J15 ohms. This is Z1. And another impedance, that is Z2, is 6 minus J8. Again, this is in ohms. Now these two are connected in parallel, and the total current entering to this is 20 amperes. So imagine that there is a current source which is pushing 20 amperes of current into these two branches. So this is the first branch and this is the second branch. Now you all know that the current will go through least resistance path. So out of these two, whichever is the least resistance, there the current will go. But then not the entire current, the remaining current will flow in the other one. So the current sharing principle will apply here. So the question is, find the complex power consumed by each branch. So in order to do that, first I will do the current division principle. So let's call this I equal to 20 and 0 degrees. So this one let's call it as I1 and this one let's call it as I2. So what is I1? So I1 will be the opposite branch Z2, proportion Z2 divided by Z1 plus Z2. So this fraction I'll multiply with the total current I, then I'll get I1. Similarly, what is I2? I2 will be Z1, that is to find this current I take the opposite branch into I divided by Z1 plus Z2. So if I do this current division principle, then I can get the two currents that are flowing there. So let me quickly calculate this. So I go back to my calculator. I'll just clear everything. So first let me define my impedances. So Z1 equal to 10 plus J15. This is in ohms. Oh, I'm sorry, J is not recognized here. 10 plus 15I. Now Z2 equal to 6 minus 8I. So 6 minus 8I. So I have defined Z1 and Z2. Now I can simply find the current. So the total current I is 20. So I need not give angle as 0. So I1 equal to Z2 into I divided by Z1 plus Z2. So this is my total current, and total current I2, not total current, that is branch current of first one, will be Z1 into this. So you notice you add these two currents. So what is I1 plus I2? So if you add these two currents, it should come back to 20. So that's what we can see here. So let me write this. So this is 2.62 minus J 11.14, whereas this is 17.3 plus J 11.14. And if I add these two, so this should be 3.8, I suppose. So then if I add these two, the total, these two will cancel each other and this will be 20 amperes. So that's again confirming. Now once I know I1, I2, what is the complex power of first branch and what is the complex power of second branch? So complex power flowing in an impedance, we can also find complex power is nothing but I1 into Z1 into I1 conjugate. So basically it is I square R, but it should be written like this because the angle of I is not important, it will cancel each other, and then the angle of the impedance will be applied to the complex power. So these are all complex numbers. Similarly, this is S1 and S2 will be I2, Z2 and then I2 conjugate. So this is my S2. So these are complex powers. So let's do that. So what is S1? S1 is nothing but I1 into Z1 into conjugate of I1. Similarly, S2 will be I2 into Z2 into conjugate of I2. So I'm getting total like this. So 1311. So this is 1311 plus 9 plus J 19.67 1967 and then 2557 minus J 3409. So you notice that the first branch is consuming reactive power, whereas the second branch is producing reactive power. So you notice if you go up, the second branch is having a capacitance here, so minus J8. That means it is producing reactive power. So if I go down, if I add this, so this will be 8, 6, 8 and 3. So 3.868 kilowatts, or this one is the watts. And then this one if I subtract, so I think I will get the net value. So let's do that. S1 plus S2 is the total power, ST, total complex power. So J1442. So this will be minus J1442. So again, if I want to draw a diagram once again, so or maybe I'll just draw it here. So this is one branch Z1, this is another branch Z2, and this is the total. So the first I want to write the active power. So the total active power P total is 3868. The total power, some 1131 is going to first branch, and then 2557 is going to the second branch based on whatever values we got. So this is watts, and this is watts. So this is the power flow, this is the supply. So from supply, the 20 amperes current which is coming, which is carrying 3868 watts of power, one that 1131 watts is going to this, and 2557 watts is going to this. Whereas if you plot the reactive power, what is happening is total reactive power generated is, so let me write it here. Total reactive power generated is 3409 watts. Reactive power is generated in this capacitor. Out of that, some reactive power, so this is Q2 equal to, some reactive power is consumed here. So that is, let me write it like this, 1967 reactive power is consumed here. This is Q1. And the remaining reactive power is going back to the supply. That is Q equal to 1442. So the fact that this is minus J implies that the supply is getting the reactive power of 1442 watts. So basically, in this short video, I try to show you series parallel circuits, how to apply Ohm's law, how to find the branch currents, and how to find the complex power, and so on. So hopefully you understood something from this problem. So if you have any doubts, please leave them in the comment section. I can discuss that. And if you like these videos, kindly subscribe to my channel. You will get more and more videos on this. As I mentioned, all the way we are going to build complexity, and we are going to analyze power system circuits also. So solving load flows and so on. Thanks for your support.